Hello everyone, my name is Ms. Shahbazi and I'm teaching mathematics for so many years. Uh, Advanced function and calculus, they are the courses that I taught so many times. I know that you are staying at home because of these coronaviruses. It's not just you, everyone are same situation, but you have this opportunity that you can learn online. We had two sessions last week and we talked about the polynomial functions. We are gonna go over it and continue the lesson. It's gonna be a good opportunity staying at home and learning new stuff and reviewing the stuff that you learned it before. I would like just to go and start the lesson. Here, before starting the lesson, I would like just to talk about the opportunity that the sorry opportunity that the OneClass Tutoring service is offering you is a 100,000 hours of free tutoring that you can sign up for it and receiving a free tutoring services one by one. That's very great, especially when you are staying at home. You do not have um a chance to go to the school or having a teacher coming to your home, then is a good way that you have a online tutor. You can sign up for the free sessions at JANINETHETUTOR.com is janetthetutor.com. It is the website that you have to go and sign up for the free tutoring sessions. Right now, I would like just to start with our lessons here. Um, we talked during the last two sessions, we talked about the character of the polynomial functions, how we can recognize if a function is a polynomial function. Especially, we talked about the pair point, how we can say based on the coordinates if a functions or based on the pair points, how set of a data if it's a function or not, finding a finite differences, finding a degree of the functions and the leading coefficient. We have learned about the degree of the function and the leading coefficient and in behavior. We learn about that, okay, how the degree of the function is helping us to do a rough graph, or how the leading coefficients are leading the functions at the in behaviors. Um, if it's starting with the positive leading coefficient, if the function has a positive leading coefficient, means that the function is gonna be end up at the positive infinity at our right hand side. If is the leading coefficient it's a negative, then the function is gonna be end up at our negative infinity, our right hand side. If it's a odd degree functions, always the hands ending hands are going in opposite direction, one of them going up, the other one's going down, or opposite directions. If it's a even degree functions, we'll learn about that. Always the ending hands are following in the same direction, both of them are going up or both of them are going down. Here, we are gonna learn more about the turning point or the zeros of the polynomial functions. Before starting to go and talk about the turning point, I like to review whatever that we learned before. It's about the maximum and minimum value. Technically, in a general way, we are naming them turning point or extreme point when we do not want to specify if it's a maximum or minimum. We know that the maximum point is the high value on y axis above the along the another point around the functions. But when we are talking absolute maximum or minimum, and absolute maximum is the highest y value on a graph, and the absolute minimum is the lowest value on a graph. We have another one, relative or local maximum or minimum. Relative maximum or minimum are the maximum or minimum that it is the greatest value of the function on its neighborhood on the points that are on that point, or the relative or local minimum is the least value of the function in that neighborhood. There's a nice graph here. I want just to zoom a little bit on it that you can see as well. I'm hoping that is readable for you. Yeah. As you see, for this graph, we have a couple of relative or absolute maximum or minimum. Here, the first point is a point A. As you see, A is a turning point, has a low y value along another y value around itself. It is minimum because it's the lowest point in this neighborhood. Now let's see if it is an absolute minimum or relative minimum. As I'm checking, this A value has a lowest value on a y along its neighborhood, not along the full graph. Then this is a relative minimum. When I'm checking B, here B is on the top, then it is a maximum. And B also is not the highest y value in this graph. As you see, I have a value in here that is higher than B value. Then it is relative maximum. Going to point C, it is a minimum value because it's the lowest y value that I can see here is a low y value in this neighborhood. And this value is the lowest in full graph. As you see, there is no other point than C lower than C. C is the lowest point on this graph. Then for C, I'm gonna name it absolute minimum. D again is a maximum, but it's still a relative maximum because I have another point higher than this D. E is also a relative minimum because we can have just one absolute in each graph. I have already one absolute minimum here and I'm done. Then this point is not as lowest point than this point, then this is a relative. Having a maximum minimum is not mandatory for each graph. Having an absolute or relative maximum or minimum also is not mandatory for each graph. See here, I have two functions here. Here, yes, I have a 1 point. It is the maximum, and technically this one is the absolute maximum because it's the highest point on the graph. But for the another one, here I can see it is the lowest point of the graph is a absolute minimum. Here I had 5 turning points in this example, 5 turning points. Just one of them were absolute minimum. Rest they were relative maximum or minimum. There is example here that we want to do it together. I already did it. We can just see the answers here. It is a graph. The extreme points are these 1, 2, 3, 4, and 5 points I have as extreme point. Some of them are maximum, some of them are minimum, absolute, or local. Here, I want to start with point -3 and -1. -3 and -1 has a low y value along its neighborhood. Then this one is gonna be the minimum. But if it's a local minimum or absolute minimum, as I have another point here, -1 and -3, lower than this point, then this point cannot be a absolute minimum. This one could just be a local minimum. The -3 and -1 is a local minimum. And as I put it here, local minimum, -1 and -3. I'm going for next point. -2 and 2 is my next point here. -2 and -2, let me just make it a little bit. Yeah. -2 and 2 is a maximum. Yes, because along its neighborhood is higher than another point. It's a maximum. But let's see if it's a absolute. I can see there's another point higher than this point, then for sure it's not an absolute. And also the function has an arrow at the end, means that it's going to the higher than these 2 points. Then neither of these points are absolute maximum. Both of them can say that they are local maximum. Here, -2 and 2 is a local maximum. Next point is -1 and -3. -1 and -3 is lowest in its neighborhood. Then it is the local minimum until this point. But when I'm checking this point with another points, all of my graph, I can see that this point is the lowest point in my graph. Then it is an absolute minimum. The -1 and -3 is the absolute minimum of the graph, -1 and -3. We already talked about the point 1 and 4. 1 and 4 also is a local maximum because it's a maximum, but function is going to the positive infinity. We are going to have a higher than this point, like a y value. Then this one is going to be local maximum. Here I have another point. Here is a turning point. 2 and a 1, as you see, is lower than another point in its neighborhood. It's gonna be a minimum, but it's gonna be a local minimum because we already had a absolute minimum. Now I'm completing this chart. It's a local maximum. Yes, I had a 2 points and I mentioned that. Local minimum. Yes, I have a -3 and -1 and 2 and 1. Absolute maximum. This function doesn't have an absolute maximum because the function is approaching to positive infinity at y value. Then this one doesn't have any absolute maximum. How about absolute minimum? Yes, -1 and -3 is the lowest point of this function. It is a absolute minimum. Okay, now we are going for the next step. It's increasing and decreasing. The topics that we are going over it is the basic that you are gonna learn it here, and you are gonna work more on your calculus if you are taking a calculus next semester or next year. Uh, Increasing, decreasing, finding a maximum, minimum, they are the topics that you are gonna see it very well on calculus. But it is good that you can learn the basic and the stuff and the definition and the picture here. Then when you are just calculating in the calculus, you are going to just calculate this stuff. You have to know this base, the fundamental that you can continue. Then it is good that you understand and make a picture, good picture of this definition in your mind that you can use it later on. Okay, we are going for increasing and decreasing intervals. Suppose S is an interval in a domain of f of x. So f of x is defined for all x value in S. F of x is increasing on S. If and if means that it's a two sides if. It's increasing if f of a is less than f of b for any value that a is less than b. Means if x value is increasing from a to b, y value has to be increased. And if such a things happen that side, I can say f of x is increasing. F of x is decreasing on a s if and if f of a is bigger than b equal by f of b for all a and b is element of S such as a is less than b. Means that if I am going from point A to B on the x-axis to the right side, my y value is coming from higher value to lower value. Means that the function is decreasing. As you see, here you have a good shape here. F of x in this one is increasing and the first shape is increasing. See, a is less than b and f of a is less than f of b. It is an increasing function. For decreasing function, it's opposite way. A is less than b is good, but f of a is higher than f of b. This one is a decreasing function. For this type of a function, we are saying that there is no increase, no decrease. It's the like a derivative is a constant. Another way for saying if it's the function is increasing or decreasing, that always I'm saying to my students in the class. When you are checking the increasing or decreasing a function, assume that you are driving on a road of this function from negative infinity to positive infinity. If I'm driving from this function, if my car is in this function or this road is gonna take me up. As long as the function is taking me up during this interval, the function is increasing. But when I'm driving, and always I'm driving from left to right. Here, as I see, the function or the road is take me down. As long as the function is take me down, then the function is decreasing. There's a couple of questions here. I'm gonna go over here. It is a parabola. For this parabola, I cannot say this function is increasing or decreasing because when I'm driving from the left side, the function is gonna take me down to this point. After this point, the function is take me up. Then this function isn't, I cannot say for this function is overall is an increasing or decreasing function. This function has an increasing interval and decreasing interval. Decreasing interval is from negative infinity to 1 because the function from the past is taking me until 1 is decreasing, and after 1 the function start to increase and take me up. I can write it down this interval in two different notation. One of them is you can write it down as a bracket notation, like interval notation from negative infinity to 1, or you can write it down as an inequality notation, x is less than 1. For increasing, it's going to be 1 to positive infinity, or x is bigger than 1, as you see here. In this function, I have a 1 maximum or minimum, and technically the maximum or minimum here is absolute minimum. As you see here, it is a 1 and negative 9 is the absolute minimum of this function. I'm going for next example. Next example is same things. Is take me up for half a way, then take me down, and again take me up. As you see, I have a 2 interval of increasing and 1 interval of decreasing. For decreasing, I can say that it's starting from negative 2 to 1, and make sure that you never put a close bracket. It's always is open bracket because specific point like here I cannot say at 1 if it's increasing or decreasing at 1, because at 1 the tangential line is parallel to x-axis and it doesn't go up or go down. Then we never include the ending point for decreasing or increasing. It's between negative 2 and 1. How about increasing? increasing, I had two intervals. One of them was from negative infinity continuing to negative 2, and the other one is going to be 1 to positive infinity. Or I can write it down as this format. In this question, as we learn here, we have a local maximum and local minimum. Because this point is not the highest point of my graph and this point is not the lowest point of my graph. They are high or low on their own neighborhood. Here I'm going to have a negative 2 and 16 as a local maximum and 1 and negative 8 as a local minimum. The next things that we are learning here is gonna be zeros of function. Zero or x-intercept or roots. Three different ways that we can talk about the roots or x-intercept of the function. The zero of a function are known also with two other names, x-intercepts and roots. A zero or x-intercept or root, you can see any of these words, same meaning, same like a usage of a function, is the value of the x coordinate where the functions cuts or just touch the x-axis. Whenever that we are passing the x-axis or touching the x-axis, we are making a 1, 0 or x-intercept. The x-intercept is the value of the x coordinates from the point x and 0. The y-intercept is the value of the y coordinates of the points where the graph crosses the y-axis, and the value is 0 and y. When I'm talking about the y-intercept, x value is 0. When I'm talking about the x-intercept, y value is 0. Let me just highlight it. As you see, x-intercept means that y value is 0. However, y-intercept, I know why there is a x value is 0. Then it's good to know that it's going technically, I can say that the opposite way. When I'm talking about the x-intercept, y value is 0 and opposite. Here there is a graph. That you can see the points a little bit. Here I want to talk about the x-intercept and y-intercept. X-intercept for this function is going to be negative 2, negative 1. Here is look like that's a halfway between 0 and 1. I just put 1 over 2. And here is a halfway through between 1 and 2 that I put 3 over 2 or 1 over 2. But as you see, the y-intercept is negative 2. If I have a function, I'm talking about the function, not relation. If I have a function, all of the functions, they do have a just one in y-intercept. We can have so many x-intercept in a function, but y-intercept for a function always is gonna be just one value. If it exists, it's gonna be just a one value. Some of the functions, they do not have a y-intercept, like a y equal by log of x. You learned that, I believe so, last year on function grade 11. Some of the functions, they do not have a y value, but if y-intercept value. But if they do have a y-intercept value, it's going to be just one value. We cannot have a two y-intercepts in a functions. Okay. Now, we want to go over some of the functions here. Investigation of whatever that we learned right now, we are putting together to see how it works. Here I have a couple of examples. They are a quadratic equation. Quadratic equation that you saw them on grade 10. You are familiar with the shape. You know what is the shape look like and what is the maximum or minimum if we have open upward, open downward, maximum we have or minimum. And we know that for quadratic, because it's open upward or open downward, always we have a one turning point. And that turning point is going to be an absolute maximum or absolute minimum. Let's see. Here I have a x squared, y equal by x squared. Degree of this function is 2, I know. But what is the number of the zeros that I have here for x squared? You know the shape of x squared, yeah? I'm just putting a very, very rough graph for x squared here. Okay. As you see here, for x squared, I have this graph. And as you see, I have just 1 0 here because it's just touching the x-axis. Number of turning point, there is a 1 and that point is a minimum. How about x squared plus 1? For x squared plus 1, it's going to be exactly x squared x squared plus 1 is going to be x squared that moved one step up. Degree still is 2, but the number of 0, I have a 0 touch of the x-axis. Then there is no 0 for this function. It's x squared plus 1. How about 3x squared minus 4x minus 1? For this function, it's going to be still a quadratic, but it's going to be 2x intercept. But all of them, as you see, they do have a 1 minimum. Quadratic function has a degree of 2 all the time. The maximum number of roots that a quadratic function have is what? How many roots can I have? The maximum things that I can have is a 2 roots. The least number of roots that a quadratic function can have, as you see, I can have a 0 roots, 1 root, or 2 roots. 0 is going to be the lowest. And the maximum number of turning point, maximum or minimum that can have it is just 1. I can have it just 1 maximum or 1 minimum. I cannot have it more than this. Here we are going for, I'm so sorry, you didn't have it this one. Yes, I was just talking about the quadratic function has a degree of 2. The maximum number of roots of quadratic function can have is a 2. I can have a 2 function, 0 or 1. And the minimum number of the zeros is 0. The maximum number of turning point is gonna be 1. I can have it just 1 turning point. Let's make it like a little bit conclusion here. A little bit. We are gonna go for a good conclusion at the end. Degree 2 have a, in any situation, have a 1 turning point. Degree point can have a 0 zeros, and the maximum zeros can make is a 2 zeros or 2x intercepts. Good. Let's go for cubic function. It's a x by power of 3. Here, for this question, you can use a Desmos to graph all of these functions to see that what is the number of turning point or what is the number of zeros. Here, here I made all of them and I just put the answer here. Yes, the degrees are 3. We are okay because the highest degree for these functions are 3. Number of zeros or like a x-intercepts here. Here, x by power of 3 is making just 1 x-intercept. Here, x by power of 3 plus 2x squared minus x minus 2, it's making 3 x-intercept. And here, this one's making 2 intercepts. The number of turning point, I'm so sorry, here looks like it's not correct. The number of turning point for x by power of 3 is 0 because it doesn't make any turning point. The shape, you saw it before. power of 3, you saw the shape was something like that. You saw it before. There's no turning point there. There is not turning point that from increasing going to decreasing or opposite direction. It is just a curving point. You are gonna learn it later. It's gonna be curving point. Then there is no turning point for this one. But for another two that I did it on Desmos, I found that okay, 3 x-intercept, 2 turning point and 2 turning point. Okay. Let's write it down for this one. Cubic function has a degree of, yes, it is 3. The maximum number of roots that a cubic root can have, the maximum is 3. The least number of root is going to be 1. The maximum number of turning point, as we see, it is 2. Cubic function is a odd degree functions. We talked about it. Odd degree functions, they do have a opposite direction at the end. If one of them is on the top, the other one is starting from down. If these two lines, if these two endpoints want to connect each other, for sure they are gonna pass the x-axis and they are gonna make at least one x-intercept. This one didn't happen for quadratic function because quadratic function is a degree even. Both hands can be on the top and they can go from top, they can come down, go back to the top and do not touch the x-intercept. And they can have a 0 x-intercept. But none of the function can have a higher than their degree x-intercept. If it is a degree 2, I can just have a 2 x-intercept. If it's a degree 3, I can have it just only not more than 3 x-intercept. Then odd degree function can make minimum 0 x-intercept because of their character that they can start from top, finish at the top, or they can start from bottom, finish at the bottom. They do not need mandatory pass the x-axis. Then they can make a 0 x-intercept. But odd degree functions, they do have an opposite direction in behavior. If they are starting from negative infinity, they are finishing at positive infinity at the y value. Then for connecting these two, for sure they need to pass at least in one place x-axis. Then for odd degree function, we have at least 1 0. But the highest degree of the 0 cannot be more than 3 or the number of the degree that I have. Okay, now I want to talk about the turning point. Degree was 2, I had a 1 turning point. Degree is 3 and I have a 2 turning point. Okay, there's a next example. I wanted to give you a chance. You go open your Desmos, draw this graph. Degree, yes, for this function, all of them are 4s, but draw the graph to see that what is the number of zeros, what is the x-intercept, and how many turning point do you have. Same time, I'm gonna do it too, and then we want to see the answers. I'm gonna just put the degrees because we know what's going on for the degrees. Degrees are 4. I'm giving you a couple of more minutes. Okay, I got these answers. Here, for the first one, the number of zeros, I got 4 zeros. Sorry. For the next one, x by power of, I got just 3 zeros. For next one, I got 0 zeros. And for the last one, I got just 1 zero. For the number of turning point, for the first one, I got 3 turning point. For next one, I got also 3 turning point. For the next one, I got just 1 turning point. And the last one, I got just 1 turning point. I'm hoping that you got same things. Quadratic function have a degree of 4. Yes, we know. The maximum number of roots that a quadratic function can have, based on a chart that I have here, 4. The least number of roots that a quadratic function can have is 0. It's an even degree, yes? And we talked about it. Right now we talked about it. I said that if it's a even degree, can like a starting from negative infinity, finishing at negative infinity without passing a x-axis, then can make a 0 x-intercept. The maximum number of turning point is 3. Then I have another example here. Degree 6, degree 4. Okay, I want just to go and answer this one because we already talked about it, but you can go and plug in a decimals this equation to see that what are the answer. Quadratic function have a degree of 5. Yes, the maximum number of roots or x-intercept a quadratic function can have is what? What do you think? Is it degree 5? For degree 4, we had a 4. For degree 3, we had a 3. For degree 2, and so on. Then the maximum number is 5. But the least number of roots, what do you think about the least number of roots? Think about it. It's an odd degree. If it's an odd degree, okay, it's starting from top, finishing at the bottom, or opposite direction. Starting from down and finishing at the top. As long as that they do have a different direction, they need to pass x-axis. They cannot just exclude x-axis. At least they need to pass one time x-axis. Then having a 1. Then the maximum number of turning point. Degree 5 has a 4 turning point. Always 1 less than whatever that we have. Oops, sorry. It looks like that I just need to write it down again. 5, 5, 1, and 4. Now let's see if we can answer degree 5 without going over whatever that I have. But I prefer degree 6 until degree 5. You saw it before. How about that if you go for degree 6, again use the decimals, try to see that if our calculation or our answers are correct. The maximum number of roots, degree 6, can have it based on whatever we talked, is going to be a 6. Degree is even. As long as degree is even, then I'm going to have a 0. I can start from top, go to the top, never hit the x-axis, and the maximum number of turning point is gonna be 1 less. They are my answer, but now I'm giving you a time. Plug these ones into the Desmos, see that what is the shape of this function. You can use a Desmos, or if you have a graphing calculator 80 like a 85, you can use any like a tools that you used before for graphing a function. I'm giving you a couple of maybe 1 minute that you can do these ones and give me the answer for here. I'm just writing the degree because we know that, sorry, we know that the degrees are 6. Okay. For the first one, number of zeros that I got here is a 1 0. And the number of turning point, I found the 1 minimum, absolute minimum. For the next one, I'm hoping that I'm not going that fast. You are following me. For the next one, I have a here 6 x-intercept, and I have a 1 2 3 4 5 maximum or minimum. For the last one, the number of zeros are 0, and the turning point, I have a 1 absolute maximum. As you see, first I answered, sorry. First, I answered this chart because I got my conclusion. I got my summary of whatever that I'm doing. If it's an even degree, it can be have a 0 x-intercept, or maximum is 6 and 5 turning point. And this chart, after drawing the graphs on a Desmos, is confirming me that I did correct. Let's see here. Here, I want to write it down a little bit about the overall conclusion. They are the good things that you can make a note. The maximum number of zeros or x-intercept that a polynomial function can have is the same as its degree. Doesn't matter if it is odd or even. The minimum number of zeros or x-intercepts that an odd degree polynomial, see, for the minimum is talking separately, odd degree and even degree. The minimum number of zeros that odd degree can have, do you remember what was it? Odd degree, opposite direction, they need to pass the x-axis, then yes, it is 1 x-intercept. But for even degree, they can have a how many zeros or x-intercept? They can have a 0 x-intercepts. I want just to having this 0 to not putting two zeros beside of each other. Now I'm going for turning point. The maximum number of turning point that a polynomial function can have is what? What do you think? We had a degree 2 with one turning point, degree 3, two turning point, degree 5, four turning point. Can I say here that the maximum number of turning point a function can have is 1 less than its degree? Or if I like to write it down mathematically, I could write it down n minus 1 because n is representing the degree of the function and minus 1 is gonna be less 1. An even degree function must have at least how many turning point? All of the even functions starting from top, finishing at top or opposite direction. Then for sure, if you are starting from top, going to the top, you need at least one turning point. But for odd degree function, like a linear function, can have a 0 turning point. Okay. Here there is a chart. Let's answer together fast. Linear function has a degree 1. Maximum number of 0, 1, because the degree odd. Minimum, 1. Maximum number of turning point is 0. Linear function, I know what is the shape look like, yes? There is no maximum or minimum on linear functions. Quadratic function, degree 2. Maximum number of 0. Quadratic degree is 2, then the maximum number of 0 is going to be 2 as well. But the minimum, because it's a degree is even, then I'm going to have a 0 as a minimum value of the zeros. Maximum number of turning point, degree is 2, 1 less than 2 is going to be 1. Cubic function, degree 3. Maximum number of 0 is always following the degree 3. Because the degree is odd, at least I'm passing once the x-intercept. And the maximum of the turning point, degree is 3. 3 minus 1 is going to be 2. Quadratic function, degree 4. The maximum number of 0, because it's degree 4, 4. Then minimum number of zeros or x-intercept, because degree is even, 0. And here is a minimum number of turning point is gonna be what? Do you remember? Is a quadratic. How many can I have as a minimum? Maximum of turning point, because the quadratic degree 4, 1 less is gonna be 3. Quantic functions, degree 5. The maximum number of 0 is gonna be 5. The minimum, because it's degree odd, at least has to be passed once the x-axis. The maximum number of turning point, 4. Degree 6. For degree 6, the maximum number of 0, 6. Degree is odd, is gonna be, degree is even, then it's gonna be 0. The maximum number of turning point, 5. For 7, I have a 0. I'm sure that you are answering the same as me, like maybe ahead of me, and then listening to my answer, and you are making sure that your answers are correct. How many minimum x-intercept, y-intercept? 1. And the maximum number of turning point is gonna be 6. In a overall, in a general, when the degree is n, the maximum number of zeros is gonna be n. But if n is even, I am gonna have a 0 as a least number of 0, and if n is odd, I'm gonna have a 1. But for turning point, always it's gonna be 1 less than the degree of the function. I'm so sorry. Oops. Sorry, I was going to the last two questions that maybe you didn't see it. Then we talked about a 7 and n. N is going to be n. If n is even 0, if n is odd, then we are going to have at least one x-intercept. And overall, n minus 1 is going to be the number of turning points. Here is like the questions that I want to give you like as an exit card, but I want to give you maybe 1-2 minutes to go over it, do it, then we are gonna do it together. The question for each of them is asking the number of 0 or x-intercept, the sign of leading coefficient, the end behavior, and finally there's some things that, okay, here, type of a function. What is the type of each function? I'm just and I'm giving you 2 minutes time. You can go. Okay, let's start to do question. I'm hoping that all of you could answer correctly. The number of 0 or x-intercept or roots. As I can see here, I have a 1 here, 1 here, and 1 here. Technically, I have a 3 x-intercept. The sign of leading coefficient, as you see, it's ending up on the right side is going to the positive infinity. Then I can see that the sign of positive is going to be a positive because it's going to the positive. How about the end behavior? End behavior, there is a two-way to write it down, one of them. X is going to positive infinity. When x is going to positive infinity, y is going to positive infinity as well. And when x is going to negative infinity, y is going to negative infinity. There is another way that we can write it down. It's based on a quadrant. I can write it down for end behavior. I'm just using another color to not mixing up here. I can write it down here, Q3 to Q1. Good? Or maybe, I'm so sorry. For end behavior, I don't want just to mix it. You can write any of this way. Now, what is the type of a function? What do you think here? What is the type of a function here? Starting from negative infinity, I have a 3x intercept, 2 turning point. I believe so. It's a degree 3. Then I can say that it is a cubic function. Let's see how did you answer for this one. X-intercept, I have a 1, 2, 3, 4. Sign of leading coefficient is ending up at the right side to the negative infinity, then the negative. And behavior is gonna be as you see, both hand is going down, then the y is going to negative infinity. Or if I like to write it down another way, is gonna be q3 to q4. What is the type of a function? What do you want to name this function? Here I can see it is a 3, there's a 3 turning point, 4 x-intercept, both hands in same direction. I like just to name this one is a degree 4, and I want to name it is a quartic. Quadratic function. There's another 2 questions here that I would like just to give you a time you do it, or maybe I can just write it down the answer and you can check with your answer later. X-intercept, I can see there's a 4 here. Here the sign of leading coefficient again is negative because it's ending up at negative infinity. Here for end behavior, I want just to follow the x one. Oops. Type of a function, again, I would like just to say that it is a quadratic function. How about here? Here I can say that I have a 3x intercept, sign of leading coefficient because ending up at negative infinity, and end behavior. Here I want to write it down based on a q that you can see both ways. q2 is going to q4, and this one, because I have it just 2 turning point, I would like just to go and say that it is a cubic function. I would like to stop here for today's lesson. I hope this one was helpful for you and you could use it. If you learned it before, you can go and like a practice more. If you didn't have this lesson before, I hope so that it was a good lesson that you could learn it. And here I would like just to stop on this one. It's gonna be a practice that I have it here, but maybe you cannot see it. I'm gonna stop it here, and you have a practice in your worksheet based on whatever that you had it in your book and whatever that you were learning in school. Otherwise, you can use a Nelson or McGraw-Hill and start to do the question regarding a polynomial character of the polynomial functions. Stay safe, stay at home, practice, and our next session is going to be a Friday in the same time. Have a very good day and bye.